So now we're going to look a little bit more about the different zones of glaciers. So glaciers are constantly gaining and they're losing ice. Snow accumulation and the ice formation occur in the part of the ice that is called the zone of accumulation. So that is this zone up here. This zone will add thickness to a glacier and it will promote the overall movement of it. This zone's outer limits are defined by the snow line or the equilibrium line, as sometimes it is called. So the snow line is going to be a zone where the accumulation and the wasting of the glacier are going to be equal. The snow line varies greatly in elevation, latitude, snowfall, seasonality, or I should say it varies with those factors. So as I gave an example before, snow line in high elevations is going to be, or in low latitudes is going to be at much higher elevations than at high latitudes, where it can be at the sea level, for example. But it's also going to vary depending on the seasonality of the place where the glacier is, as well as the snowfall that it receives. So the zone below the snow line is called the zone of ablation or the zone of wastage. So this is going to be this area right here. In this zone, there is a net loss to the glacier as all of the snow from the previous winter melts. So along with also some of the glacial ice. Snow lands on top of it. It typically melts and flows either on top of it or kind of moves in between the crevices, or the ice itself at the mouth, if you would, at the terminus of the glacier will also melt. So ablation is the loss of glacial ice. That's the term for it. Ablation, loss of glacial ice. In addition to the melting, it also encompasses calving. So calving happens when large pieces of ice will break off the front of the glacier, that terminal part, I guess, over here. So this calving usually happens when the glaciers are attached to the sea, or they become some sort of ice shelves or outlet glaciers. So the calving causes, or it creates icebergs in places where, again, the ice reaches the ocean or a lake. So calving is the main way in which ice is being lost in Antarctica, for example, as we saw in the example of the whole ice shelf Larsen B detaching. It made many icebergs float onward to the Weddell Sea. So as the icebergs are detached and then they flow within the sea currents will carry them elsewhere, and then they will start to slowly melt. When they melt, they will start to drop the sediment that was encased within that ice. And when the sediment is dropped and it sinks to the bottom, it can have been carried for hundreds or even thousands of miles from wherever the glacier actually eroded it from. So these type of sediment that gets dropped by the iceberg as it flows and it melts is called drop stones, okay? So it would be somewhere in here, ice melts, drops a stone, so it's called a drop stone. So whether a margin of the glacier is advancing, retreating, or it's remaining stationary will depend on the overall budget of the glacier. So this glacial budget is the balance or lack there of balance between the accumulation in the upper part of the glacier and the ablation in the lower part of the glacier. If the accumulation is greater than the ablation, then the glacier advances and it grows. If the ablation exceeds accumulation, then the glacier retreats and starts to shrink. It's also super important to point out that glaciers will continue to flow forward regardless of whether it is stationary, advancing, or retreating. The flow of the glacier will always flow forward regardless of what it's doing. So in the case of a retreating glacier, for example, the ice still flows forward, but not rapidly enough to offset the ablation effect. Glaciers are pretty sensitive to changes in temperature, as many of you know, as well as changes in precipitation. So they are great at providing clues in the current climate at which they are formed, as well as, again, any past climates from which they keep a record. So with a few exceptions, valley glaciers around the world have been retreating at rates that are unprecedented, at least according to us humans. Many glaciers have in fact completely disappeared. For example, in Glacier National Park, which is in Montana, about 150 years ago, there were 147 glaciers. Now, there's only 37 glaciers remaining. Another example is the one from the images in the bottom right that you have over here. The images to the right show a 78-year span of a glacier in the southwest coast of Greenland. So you see a main glacier with some tributary glaciers on the side. In 1935, it was flowing just fine. And then 78 years later, you have no longer a main glacier, and then you still have the tributaries, but they're flowing into basically what is now a lake. The picture on the middle also shows the retreat of glaciers. So it shows a sign marking the location of the front of the glacier almost 40 years ago. And then you see people walking through what used to be the basal part of that glacier up all until they meet the glacier up here. So many, many meters of retreat that glacier has seen. So overall, we are seeing glaciers retreat on average in the world right now. So now that we have covered glaciers, the different types of glaciers, the ways in which they form and the ways in which they move, as well as the rates in which they can move, we're going to cover the glacial erosion and then the glacial deposition. So overall, glaciers are great at eroding. You only need to look at the sediments, for example, that have been deposited at the end of glaciers when they melt to see the quantity of material that glaciers indeed have eroded above. Granted, some of this material has also kind of fallen onto the glaciers from above by some mass movement process, meaning some sort of landslide or rockfall, for example. But a lot of the material that they still carry comes from the glaciers scraping, scouring, and then the tearing apart of the rock through which they're flowing, or on top of which they're flowing. So ice is also probably the best carrier in terms of its competence. So remember, competence is the ability to carry large size material, and it's also probably the best in terms of the capacity of the glacier. Remember, capacity is the ability to carry large loads of material. So ice is both capable of carrying large loads and also load that is very big in size. So there are two main ways in which glaciers can erode. They are plucking and abrasion. So plucking happens when glaciers flow over a fractured bedrock surface. And by frost wedging, which we looked at in chapter 6, if you remember, it was a type of physical weathering. The glaciers will fracture, they will loosen, and then eventually with their flow, they will lift up the blocks of rock, and then they will incorporate them into the ice and into the flow of the glacier overall, like you're seeing in the picture over here. So this would be the plucking taking place, plucked boulders. The second major erosional process is called abrasion, and it's similar to the abrasion that takes place inside of a stream of running water. As the ice and its load of sediment slide over the bedrock, they will smooth and they will polish the surface below, kind of like a sandpaper. So the pulverized rock resulting from this polishing is known as rock flour, as you're seeing over here. And it is this rock what gives kind of that cloudy to milky appearance that many of the streams that are fed by glacial meltwater have. So these bodies have this kind of like turquoise look to them. So the picture right here is a picture of the meltwater from a glacier that is feeding into a greater either trunk stream or lake. It's kind of hard to tell by the picture. And then This picture right here shows the actual pulverized rock, which we call rock flour, that later goes on to meet the meltwater and flow into streams or lakes. So also, when there is abrasion on the bedrock by the glacial ice, along with the sediment, if this sediment is made out of large rock fragments, sometimes the big rock fragments are going to make these long scratches and grooves that are left on the bedrock through which they flow. So these are called glacial striations, and they appear just like the ones that we see here in the bottom right. So as you can see, the striations also tell you something about the flow of the glacier. It gives you two possible directions of flow. In this case, the glacier was either moving kind of up into the slide or up above the slide, or it was flowing kind of down below the slide. So it gives us an idea of direction of flow. Also remember, when we covered chapter 2, it was thanks to some of the glacial striations that Alfred Wegener was able to propose the idea for continental drift. It was one of the evidences that he used for continental drift hypothesis in the early 1900s. And we'll refer to this again later in the chapter. The rate of glacial erosion is going to be highly variable, of course, and it is controlled by 4 main factors. So those are going to be the speed of the glacier's movement, the ice thickness, the shape, abundance, and the hardness of the rock fragments at the base of the glacier, and then the erodibility of the surface that is beneath the glacier. So these 4 factors vary from location to location, and they vary in time as well, which will result in different landscapes that are formed by locale. So, for example, if I have a glacier that is moving faster rather than slowly, it will perhaps not erode as fast, but it will definitely carry the sediments faster. If I have a surface through which the glacier is flowing on top of that is made out of unconsolidated sediments, then the glacier is going to be better at eroding those unconsolidated sediments. If I have a glacier that is carrying with it a lot of sediment already that is rather angular, then it is likely that I'm going to be doing a lot of abrasion and a lot of plucking rather than not as much if the glacier isn't carrying much sediment already. Okay, so these are just ideas as to how those 4 factors are going to change the capacity to erode of a glacier. The erosional effects of valley glaciers and of ice sheets are quite different. The alpine or valley glaciers tend to accentuate the irregularities of mountain landscape, and they create steeper canyon walls and make these kind of jagged looking peaks. By contrast to these, the continental ice sheets generally tend to override the terrain, and they will then subdue it rather than accentuate the irregularities that they encounter. So because of this, typically the landscapes that are shaped by valley glaciers are a little bit more inspirational than those made by ice sheets, or I think that that's the case for most people, that they feel more inspired by the landscapes made from valley glaciers. So we'll cover all of the landforms that I have listed right here in the slide. Most of them can also be seen in the diagram on the right of the slide, which shows the progression of the landscape formation. So here you have not a glaciated terrain, then you have some glaciation going on. You start seeing the topography kind of start getting a little bit more accentuated. Once there is a glacial retreat, you end up with the remaining topography, which again accentuates the irregularities of that terrain in a valley glacier type setting.